20. Alright guys, this is a fairly simple one. What you just have to recognize is that you actually have to factor. So if we look at this, it says the limit as t approaches 2, okay, of t squared minus 3t plus 2 divided by t squared minus 4. Alright, so what we notice is if we plug 2 in, what's going to happen?
It's going to equal 0.
Over 0. So you're going to get 0 over 0. So there's an issue there. Now, typically, what you want to keep in mind is if you get 0 over 0 and it's a quadratic function like this, like we have quadratic in the numerator, quadratic in the denominator, you probably want to factor it. Okay? So what we can do here is we can rewrite this and say the limit as t approaches 2 is equal to t minus 2 times t minus 1. Okay? And then t squared minus 4 factors into t minus 2 times t plus 2. Alright? Why do we do that? Because we plug in the 2 here, and we get 0 over 0. So we know there's something that's causing this to be 0 when I plug 2 in. So like, since it's quadratic functions in the numerator and denominator, that tells me that there's a factor that's making it equal 0 when I plug 2 in. So I know that I need to factor both the numerator and denominator. And one thing I can do is, since I'm plugging 2 in and it's making it equal 0, that should tell me that it's probably going to be something like t minus 2 that's making it 0, because 2 minus 2 is 0. So what I have is that cancels out with that, and I'm left with this equaling the limit as t approaches 2 of t minus 1 over t plus 2. So now I can plug 2 in. 2 minus 1 is 1. 2 plus 2 is 4. So I get 1, 4. Make sense?
Yeah.
Right? So always look at factor stuff. Okay? Now, what we're looking at next is number 22. Okay? So, we look at 22. It says the limit as x approaches 0 of 1 over 2 plus x minus 1/2 all over x. Okay? So what I have here is I have a fraction over a fraction. So I have the fractions in the numerators, and then I have that whole thing being a fraction. Alright? So, first thing that we need to know is, I want to make this numerator more simple. But I can't make the numerator more simple because I can't combine it because the denominators are not common. So I need to make these like denominators. So the way to do that is, well, I see this is 2 plus x, this is 2. Alright? Easiest way to do that is just to multiply this by 2 over 2 and this by 2 plus x over 2 plus x. So what I'm going to do, I'm going to do some work off to the side. Okay? So some work off to the side, and I'm going to go 1 over 2 plus x. I'm multiplying that by 2 over 2. And over here, so that's going to give me 2 plus 4 plus 2x. And then I'm going to multiply 1/2 here. So it's going to be 1/2 times 2 plus x over 2 plus x. Alright, so that's going to be equal to 2 plus x over 4 plus 2x. So notice the denominator is the same in both of those now. Alright, so that's my side work. So back over to here, I'm gonna have the limit as x approaches 0, okay? So I'm gonna have 2 over 4 plus 2x minus 2 plus x over 4 plus 2x. This whole thing's over x. Following along so far? So at that point, I can combine what's in the numerator. So 2 minus 2, that's 0, so that cancels out right there. And I'm left with minus x. So I have the limit as x approaches 0 of minus x over 4 plus 2x. All right? And I'm going to rewrite this a different way. Since I'm dividing by x, that's the same thing as multiplying by 1 over x. Okay, so I'm just making that a little bit easier to see. Okay, so at this point, I can combine this into one fraction. So that's going to be the limit as x approaches 0 of negative x over 4x plus 2x squared. All right. Do you see anything that can cancel out here? X's. So this x is going to cancel out with this x and one of these x's. So I'm left with the limit as x approaches 0 of negative 1 over 4 plus 2x, which is going to be equal to negative 1 over 4. Right? Yes? Yeah.
Why did you do that?
Because I plugged in 0 now, so 2 times 0 is 0.
Oh, okay.
Alright? So it is a lot of work. On my paper, I simplified it and combined some steps, but I just want to show all the steps here. Okay? So that's a good review of what to do. So usually, if you have, anytime you have a sort of complex fraction, where you have fractions inside of fractions, you're always going to want to take the numerator, all right? Try to simplify it by making the denominators the same, and then multiplying by whatever's in, just taking the division and turning it into multiplication, all right? So, are there any other questions about homework?
How would you do the beginning of next week? And x minus 1 over x squared minus 1.
So that's just, if you look, if you plug 1 in, you know it's going to be 0 over 0. Now that means that something's going to factor out. So,
X is factored out?
so no, not x's. So you have, what does x squared minus 1 factorize?
X minus 1? Not x minus 1?
Let's say x squared, let's say
X squared minus 1?
x squared minus 1. That's going to be x minus 1 and x plus 1.
Okay.
And we should see stuff cancel out. Alright? So, what I want to do is, this is solving stuff algebraically. Okay? We're finding the limits algebraically. What I want to do is continue looking at some more examples of this, and we actually need to look at some properties of limits. So we are going to take some notes right now. Again, even if you didn't finish all of your homework, you're still going to turn it in today. I'm going to grade it, whatever grade it is on there, maybe 3 out of 5, 4 out of 5. You can then, when you get it back, complete the homework, show me, and then I'll give you the points. Does that make sense?
You said what?
As long as I want you to turn your homework in, even if you aren't done, and then at that point, I'll grade it, give it back to you, and you can always complete it to get the rest of the points. Okay? So, what I want to start at, All right, these are some limits that you need to memorize. All right, that you definitely want to know. All right, so what we're going to do is, and then we remember what this first limit, the limit as x approaches 0 of sine x over x is. 1. All right, so we know that it's 1, but I want to talk about something real quick. That's 1. All right. Something that's very nice about this is we can actually take this and rewrite this and say that we're going to change u. We're just going to represent this x and say sine u over u. All right, where u is anything. All right, and so what we get is the limit as u approaches 0, sine u over u, right? This is equal to 1 as well. Okay? And the key here is if you have sine u over u, where u is, someone tell me what you want u to be. Well, it's not 3. I mean, like, let's say 3x. So let's say u, we say u is equal to 3x. All right? Well, then we got the limit as 3x approaches 0 of sine of 3x over x, or 3x equals 1. So what we're able to say is, if you have sine of 3x over 3x, it's equal to 1. If you have sine of 4x squared over 4x squared, it's equal to 1. All right, so it allows us to make that generalization, which is going to help us later on. All right. So again, to talk about what that, just to refresh you guys about what the graph looks like. It looks sort of like a cosine graph, but then instead of having a amplitude of 1 all the time, comes down and then it starts dampening at the end and just keeps getting smaller and smaller amplitude on both sides. Alright. Now, the limit as x approaches 0 for x over sine x is the same thing. Alright? It's 1 as well. And you can do the same exact type of thing as we talked about with sine x over x. You can have, this says 3x over sine 3x. It also equals 1. Okay, so you can continue doing that same thing. Alright, and for that graph just looks like a little bit something like this, where that, and then that, that. So there's just a bunch of U-shaped, upside down U's, right side up U's that continue, and there's just a bunch of vertical asymptotes, like all over the place. It's a vertical asymptote party. So, do you need to know what that graph looks like? Not really. I don't believe you're going to need to know exactly what that graph looks like any time, but it's good to know. All right. So, are they becoming backwards? Well, because, so, this one looks like this, because both of these, if I plug 0 in, I get 0 over 0, which tells me there's a hole, Alright, now this one, sine x, you got to move 0 over 0 as well. My best explanation for this is that if you look at this graph, sine, the only place this is going to equal 0 over 0 is at x equals 0. But this place, this right here is going to be undefined in a lot more places, because sine x equals 0 at 0, it equals 0 at pi, it equals 0 at 2 pi, it equals 0 at 3 pi. So the explanation here for that, that's a good question. is that this place, or this function, is gonna have a lot of vertical asymptotes because there are a lot of places where there's a lot of xi's where the denominator is gonna equal 0. Alright, so like, this vertical asymptote here equals 0 over here, or the denominator equals 0 over here, over here, over here. So that's a good question. Alright. So, let's move to the next page. Alright. So, the constant multiple rule. So these are properties and limits. You want to write these down. You want to know how to use these. These allow you to find the limits of property, or these allow you to find the limits of functions very quickly using some shortcuts when you have a function that looks more complicated. Okay. So the first one is called the constant multiple rule. Okay. So what this says is if you have the limit, okay, the limit as x approaches a, right? We just say a for any number x, and you have c times f of x, where c is a constant. All right. Then this limit is just equal to c times the limit as x approaches a of x. Alright? I'll show you how to use this in the examples following these properties right here. Okay? It's very simple. It makes it easy. So like when you see a function that looks complicated that you don't necessarily recognize, alright? So for instance, one function that we are going to that could make this could make it easier to find the limit of is when you have let's say 4 sine x over x. We know what sine x over x is, but we don't know what 4 sine x over x is. And you'll see, and so what this allows us to do is it's just going to allow us to pull this 4 out. What's the limit of sine x over x? 1. So it's 4 times. So really, what this is saying is 4 times sine x over x. This is bad notation. So it'd be 4 times 1, which would be 4. Yes. All right. So we'll see some more examples of that. That's horrible notation. All right. So don't just not write the limit, but you have to actually write the limit to say what you're doing. So the next one, sum and difference of limits. Okay. Sum and difference is typically what operations? Yes. Adding and subtracting. So what this allows us to do is, let's say you have the limit as x approaches a of f of x plus or minus g of x. Alright, I put plus or minus because it could be f of x plus g of x or f of x minus g of x. Alright, and that is going to be equal to, what this allows us to do is say, okay, we can take this and break it up and say the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. So let's say we don't know how to find the limit of a certain function. So if we look at it, it looks like we know how to find the limits of pieces of it. Well, we can just break up those pieces into their own limits so that we can easily find the limits that we know. And again, you guys, we'll see some examples of that. All right, and if not, then we'll make sure we do. And then finally, we have try the quotient of limits. What do you think this involves? Multiplication and division. Alright, so what this allows us to do is to say we have the limit as x approaches a of, let's say we have f of x times g of x then this is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. Okay? Quotient of limits allows us to say that limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Alright. Is there some examples? Alright. So this is really going to be fairly, I think you guys will find it's pretty simple. Alright. You just, what the issue is, you just have to get used to knowing which property to use. Sometimes it might not be 100% obvious which property to use, and you might have to mess around with something. Alright. So, here we go. So we're going to start at the top. Alright. These are actually using the properties and the idea that you guys now have memorized. The whole, that you guys have memorized, the limit of sine x over x as x approaches 0, and the limit as x approaches 0 of x over sine x. Alright. So we're using those two limits and the properties to figure out these limits. Alright. So if we look at the limit as x approaches 0 of sine x over 4x, any ideas of what we're looking at here, like what we might do to find this limit?
You want to read?
So, yes, we're going to need to use one of the properties. What else does this look like we probably are going to need to know?
The one with the sine x over here.
So, we see sine x over x, but it has a 4 here, right? So, this 4 is just, it's a number, right? It's a constant. Do we have something that allows us to take constants and take them outside of the limit? The constant multiple rule. So really what this is saying is if we rewrite this, and we look at what this is actually saying, it is saying the limit as x approaches 0, when I divide by 4, that's the same as multiplying by 1/4. So really this is saying limit as x approaches 4, 1/4 times sine x over x. So, using the constant multiple rule, like Michelle said, we can take this 1/4. Because we're really right here, it's sine x divided by 4x. So that is just 4 times x. So really, it's sine x divided by 4 times x, so divided by 4 and x. So I can bring this divided by 4 and by 1. So I can bring this 1/4 out now. So what I have is I have this is equal to, oh, not really, this gives me 1/4 times the limit as x approaching 0 of sine x over x. Now, do we know what the limit of sine x over x is as x approaches 0? 1. So this is equal to 1/4 times 1, or 1/4 times 1. 1/4. So this limit as x approaches 0 of sine x over 4x is equal to 1/4. Pretty straightforward.
Wow.
All right. So down here, what is the limit as x approaches 0 of sine pi x divided by x? What is this looking like? Okay, so this kind of looks like sine x over x, correct? But there's a pi in here. Now, the issue with this is, okay, well, let me just ask you, what do you think we might do? What do you think we might do?
Get the pie out.
Okay, so get the pi out like you did with the 1/4. Here's the issue. You can't take a pi out of this because it's sort of locked in. It's sine pi x. You can't take the pi out. So here's the issue. All right, I'm going to pose a question. All right, we just talked about back here that we can say we can take this and rewrite sine x over x as sine u over u. Right? The issue is, and no issue, where u is anything we want it to be. And the only thing that needs to happen is u needs to be the same as u. So right here we said sine of 3x over 3x is equal to 1. Alright? So would sine of 3x over x be equal to 1? No, because u isn't the same. But as long as the u is the same, we're good. So here's, in a sense, my u is what in this case? So I'm saying u is equal to pi x. Well, I need this denominator to be x. So what would I have to do? Not add. I'd have to multiply by pi. But here's the issue. I can't just, if I multiply by something, it has to be equivalent to 1. I can't just multiply by 1 over pi. That's changing the whole problem. So what I have to do is I have to multiply by pi over pi. Because pi divided by pi is technically 1. Right? Pi divided by pi is 1. Because anything divided by itself is 1. So technically it's 1. It just doesn't look like 1. It's a fancy way of writing 1. Alright, so what I'm going to do here is I'm going to say, okay, the limit as x approaches 0. And I'm going to multiply this whole thing by pi over pi. So that's times sine of pi x over x. So what that is equal to is the limit as x approaches 0 of pi sine pi x over pi x. Now, we follow along so far?
Yeah.
So now I have, remember we said u is pi x, right? So I have sine pi x over pi x. So what's sine pi x over pi x equal to? What is the limit of that? 1. However, we have a pi here. This pi is a constant. So limit, now what would I do with this pi? If it's a constant. What did I do when I had a constant out here? Well, what did I do with this constant that's in here? I took it and I removed it out and put it outside with using the constant multiple. So if I have limit times where I have the limit of x approaches a of a constant times a function, I can pull the constant out, and then I can go from there. So this pi is a constant. So I'm taking this pi, and I'm pulling it out. So I have pi times the limit as x approaches 0 of sine pi x over pi x. So, what would the limit be of this function, sine pi x over x? Pi times 1, which is pi. Now, could anyone want to take a guess as to what this next one would be?
Like we don't do like that one.
You have to do it like the second one
No.
up here?
Uh-huh. No, at the bottom. No, it's the one. That's the one. Did you hear that 3?
So if this 3 was not here, this is x over sine x, it would be 1, right?
Yeah.
However, it says 3x. So, remember what I said, that one's just like this one we just did. As long as this said 3x over sine 3x, it would be 1. So what do I need to do to this numerator? I need to get a 3 up there. Now, the only way I can get a 3 up there is if I take that and do what I did here. I multiply by pi over pi here because I need to get a pi in the denominator. So now I need to get a 3 in the numerator. So what would I multiply by? 3 over 3 because it has to be equal to 1. So I have the limit as x approaches 0 of 3 over 3 times x sine 3x. That's going to give me the limit as x approaches 0 of 3x over 3 times sine 3x. What do I have here? Yeah, get where we are. Everyone get where we are now. We have the limit as x approaches 0 of 3x over am I multiplying by 3 here, or am I multiplying by 1/3? Because this 3x, so the bit what you're saying, now what I'm saying is really what this is saying is this is equal to the limit as x approaches 0 of 1/3 times 3x over sine 3x.
No, you had to bring out that 3 in front of the limit.
So, yeah. So, I mean, when you guys get, obviously, you get rid of this, you don't need to show all the steps, but yes, I'm going to bring the 1/3 out. But what I know is, like the bit said, he was just reading it wrong. He said 3 times 1 is going to be 1/3 times 1. So you can pull the 1/3 out. So you have, this is equal to 1/3 limit as x approaches 0 of 3x over sine 3x. 3x, the limit of 3x over sine 3x is equal to 1. 1 times 1/3 is 1/3. All right? Alright, so, question on this. See, these are just like, it's just like little tricks and manipulation. That's one of the few things that makes calculus hard is that there's a lot of, sometimes you just have to manipulate an equation or a function in a weird way, or a simple way that's not quite obvious to make it workable. Alright? So like here, all we're doing is multiplying by 1, but we have to multiply by 1 in a weird way. 0 to 3 with pi and pi. Alright? So, hold on, change the limits, guys. You're up here now. Alright, so looking at this first one. Can you guys tell me what the limit of that is right now? Why not? So, okay, let me ask you this. So could we figure out the limit as x approaches 0 for x squared? What would we do? No, I know that.
Wait, what did you say?
Can I find out how would I figure out the limit if it says limit as x approaches 0 of x squared? Good, I just want to 0. Do I know the limit as x approaches 0 of sin x over x? 1. Do I know the limit of as x approaches 0 of 4? 4, which is a constant. So I know the limit of this, I know the limit of this, I know the limit of this. It almost seems like if I could break it up, it would be 5 over 4. You want it. Well, how would you get 5 over 4? So what's this? It's not 1, that's 0 is. So we're thinking it'd be 3, because you're thinking the right way. You're thinking that there's this minus sign in front of that 1, so it's minus 1 plus 4. So it'd be negative 1 plus 4, which would be 3 now. So we'll make that as an educated guess. Here's, so just looking at this, we're like, okay, we know this, this, and this, and then we just add them, so you know it's going to be like maybe 3. Let's check though, because I want to make sure we're right. So how can we prove this? It almost seems like we should probably be able to break it up using some properties of the sum and difference of limits. Right? So the sum and difference property of limits says that we can take a complex function looking like this, break it up, so that way I take the limit of one thing, subtract the limit of another, and add the limit of another. So what this allows me to do is take this and go, the limit as x approaches 0 of x squared minus the limit as x approaches 0 of sin x over x plus the limit as x approaches 0 of 4. Okay, so you guys have already told me what this is. So look here, what's the limit as x approaches 0 of x squared? 0. And how do we get that? You just plug 0 in front, so you get 0. So 0 minus, Michelle, what's the limit of sin x over x as x approaches 0? 1. We know that. Why? Because I told you to memorize it.
Okay, you want a little answer?
That is the real answer. Alright? And then, the limit as x approaches 0 of 4 is just what, Shamar? 4. Because it's a constant. So that's plus 4. 0 minus 1 plus 4 is 3, just like you said.
Honestly, I saw most questions, so hard.
Good, I'll take that. What, just by plugging them in?
Yeah.
That's really, I mean, that one's pretty easy, like, there's other ones, like, when it's just like a, you could do this for, like, when you have like x squared plus 4x plus 5, you can break it up if you really want to, but you don't have to because, you know, you can have just plug it in. However, this one looks a little bit more challenging. The limit as x approaches 0 of 5 sine x over 2x plus cosine x. Okay? Look at, what do you guys see in this? So you see sine x over x looks like a 5 by the sine, a 2 by the x, right? Plus the cosine x out back. I mean, that's not, the cosine x is easy. So what can we do here? Okay, so first thing we might do is see, okay, well, I have this function 5 sine x over 2x plus this function, which is cosine x. Let's break them apart. Maybe that makes it a little bit easier. So let's see, the limit as x approaches 0 of 5 sine x over 2x plus the limit as x approaches 0 of cosine x. Alright. Any wild guesses here what this limit might be yet? Do you guys see anything else I can do to break this apart some more and make it so that we have limits of only things that we can? I am multiplying sine x over x by something. And what am I multiplying sine x over x by? 5 over 2. So it sounds like what you're saying with it is that this is good. Because it's 5 over 2 times sine x over x. So why not? So this is going to be equal to 5 over 2 times the limit as x approaches 0 of sine x over x plus the limit as x approaches cosine x. Awesome. Okay, so what is the limit as x approaches 0 of sine x over x? Why? Yes. So it's 5 over 2 times 1. 5 over 2 plus the limit as x approaches 0 of cosine x. What is cosine of 0? One. This is 1 because cosine of 0 right there, 1 unit away. So it's 5 over 2 plus 1. Can you do that? Good. 7 over 2. 5 over 2 plus 1. That's equal to 5 over 2 plus 2 over 2. Alright, so, we have one last problem to look at, right here. Remember, we got another 40 minutes. So, let's look at this. So we have the limit as t approaches 0 of e to the t. Times t, x, I can use b, c, d. No pluses here, huh? And there's an invisible plus sign over there. What happens when I start writing? It shows up. So, this one is. So then what do you do? What's e to the 0 power? What's e to the 0 power? One. So, I claim that this problem is so easy that we don't even really need to do any of the problems. Okay, so the only property that I would say you could use here is, okay, yeah, this might look complicated, but what we can do is say the limit as t approaches 0 of e to the t times the limit as t approaches 0 for tangent of t. Okay, so e to the t power is equal to 1 times, as Levent looked on his calculator since he doesn't have the unit circle memorized, tangent of 0 is equal to 0. 1 times 0 is 0. Yeah, the unit circle goes on.
I'm saying that.
The tangent of t is 0. It is the y value divided by the x value. So the sign of 0 is 0, the cosine is 0, 1 is 2. All right. Congratulations. We are not done. Crazy.
Oh, I thought it was 0, but it's 0. I'm like, I didn't think.
Theta.
I see it's the theta more.
Well, good thing you have a smart board, because Ava can draw theta for anything.
All right. What do we do, Levin?
You the 3 over the negative 3 over the 8.
It's a good idea, but I can't because there's no 3 in front of the sign. There's a 3 in front of the sign after. So I can't just take this 3 and this negative 2 that's under everything and move it out front. Now, I do like this idea though, but I need to do something first.
About 3 times 8.
Let me give you guys a hint. Okay, this is essentially like I took 2 fractions and made it into 1. Now I have 1 fraction. So I'm gonna rewrite this.
Like 3 over negative 2 theta.
I can do 3 theta over negative 2 theta. So I can have the limit. Limit of theta goes to 0. And then what here I think she's saying is I can go 3 theta over negative 2 theta plus sine theta over negative 2 theta. So all I'm doing is I'm breaking up the numerator into 2 fractions. Now, what can I do here? So then you get some pretty good ideas. What might be the first thing I want to do though? Before you start pulling stuff out. I'm adding these two. This is a function and this is a function, right? So I'm gonna go ahead and use the, addition property for this, alright? So, well, I guess I need the sum property. Alright, so what I have here is I have the limit as theta approaches 0 of 3 theta or negative 2 theta plus the limit of as theta approaches 0 of sine theta over negative 2 theta. Alright, now look at this. What did you want to do at the very beginning?
Move the 3 and then move to the front.
You're gonna make it to the front, alright? So, I'm gonna have so negative 3 over 2 times the limit, theta approaches 0 of theta over theta plus, can I bring anything out front for this one? Well, is it a negative? Is it a negative 2? No, is this a negative 2 right here? It's a denominator, right? So it's not negative 2, it's
Wait, oh, I have something about that.
yeah, there you go. 1 over negative 2, so it's negative 1/2. So I'm going to pull negative 1/2 out, multiply that by the limit as theta approaches 0 of sine theta over theta. Alright? I see something that makes our life a little bit easier. Let's go through this. We have negative 3 over 2 times, what's theta over theta? 1. So it's the limit as theta approaches 0 of 1, which is, what's the limit of that? What is the limit of, so this is really, that's really a 1.
Oh,
So the limit of that is 1. Alright, so plus negative 1/2 times what's the limit of sine theta over theta? 1. Alright, so I have negative 3/2 plus negative 1/2 or minus 1/2. So negative 3/2 minus 1/2 is equal to negative 4/2, which is equal to let me ask you guys this. I know. I ain't gonna help you today. So we look at this next one. Sine, or limit of k approaches 0 of sine k over k plus 1. Do I even really need to use properties?
I believe that is true. Yeah. So sine k over k is 1, and then plus 1 over.
Okay, so that's not sine k over theta, that's sine k over k plus 1. What is the value of sine? What happens if I just what? So it's okay, so sine k over k plus 1. What happens if I put this in the numerator and denominator? So it's what sine, so if I put 0 into be sine 0 over 0 plus 1, what's but Shamar, yeah, 1 over the denominator, what's sine 0? Cosine of 0 is, so sine of 0 is 0 over 1, so this thing is 0. I guess, you could, I mean, if you want to really, maybe you're struggling there, right? You could break this up to where you have the limit as k approaches 0 of sine k divided by the limit as k approaches 0 of k plus 1. But that's really doing a lot more work than what you need to. In fact, if I'm finding limits, the first thing I'm going to do is probably do substitution just to see if I can. Alright? Alright. Questions? I'm not going to get through.
Good, that's great.
Alright, so what we've been talking about are limits, like solving them algebraically, and it's always been about, like, you know, they're approaching some number that we can actually, like, visualize and see. Alright? But what happens is we have a lot of these functions that have asymptotes. Alright? And when that happens, you get functions that have limits where they are approaching infinity. Right? Which leads us to the topic of conversation, limits involving infinity. Alright? And this is going, the first time that we're going to see limits involving infinity it's still going to have x approaching a certain value, but it's going to be approaching a value where there's a vertical asymptote. Okay? So, looking at this problem, we have the limit as x approaches 3 from the right. We want to find the limit of 1 over x minus 3 as x approaches 3 from the right. Alright? So, so we have two ways of doing this. Okay? One way is you can graph it. So I'm going to quickly sketch the graph of it. So this is the same graph of 1 over x, and it has moved 3 units to the 1 over. Good. All right. So that's fine. So there's a vertical asymptote at x equals 3. And what we can do, anyone know what the graph looks like? This 1 over x. Alright, so here's our graph. And this asks, again, the limit as x approaches 3 to the right. So we are looking at this side right here. So if we look at this, the limit is like really good at like on this. What is this function approaching as we get closer and closer to 3 from the right? Good. Then we're going to keep going up forever. So it's approaching positive infinity. Okay, so the one way is you can graph it. Now you guys can graph it on your graphing calculator when it's a more challenging function. This one's easy enough where we can just quickly graph it by hand without having to think too hard. Okay. Now the second option is by looking at a table. Okay. So what we want to ask ourselves is to make an x, y table. All right, and we want to approach 3 from the right. So who can give me a number that is close to 3, like that's really, really close to 3? On the right hand side. 4, you said? Maybe we'll go 4. I want to get closer though. Well, 2.999 will be on the left hand side.
Okay, 3.001.
Okay, so let's start here. Let's go 3.1, 3.01, 3.001, 3.0001, and for the heck of it, let's just go one more. 1, 2, 3, 4. Okay, just for the heck of it. All right, now what we're gonna do, and let's see, I'm just gonna use one of your guys' calculators. Well, I have one. Let's plug 4 in. So if I plug 4 in here, I'm gonna get 1 divided by 4 minus 3. 4 minus 3 is 1, so 1 divided by 1 is 1. Now if I plug 3.1 here, I'm gonna get 1 divided by 3.1 minus 3, where that's gonna be 1 divided by 0.1. So if you, on your calculator, 1 divided by 0.1, what do you get? 1 divided by 0.1, you get 10. Cool. Oh yeah, that'd be blasting off the
You get 1 divided by
0.1.
1.
You get the third. 3.1 minus 3 is 0.1.
Okay.
So it's 1 divided by 0.1. Now, I'm going to do 3.01. So 3.01 minus 3 is 0.01. So what is 1 divided by 0.01? 100. Oh, okay. It looks like it's getting big. So, you think? So this is, so it's going to be 3.001 minus 3, that's going to be 0.001, so what's 1 divided by 0.001? 1,000. So then what's the next number going to be? 10,000, and then what? 100,000. Okay, so just looking at this table, does it make sense to say, okay, this is going towards 1,000 or a million or infinity?
Yeah.
Yeah, because clearly it's getting big really fast. All right, the next one will be a million, then 10 million, then 100 million, then a billion. You're getting up there very fast. All right, questions on that? All right, so let's look at another one real quick. So we have 1 over 2 minus x plus 3. We are going to and hold this over real quick. So why don't you guys go ahead and graph that on your calculator, 1 over 2 minus x plus 3. So 1 over 2 minus x, and then plus 3. So and before you can graph, it should look like
2 minus x is 2x.
2 minus x. So before you hit it, it should be like I'm actually going to go 1 divided by 2 minus x, just to be on the safe side. Alright, so 2 minus x, and then I'm going to close all these parentheses, and then hit plus 3. And then graph it. So there's our graph. All right. So looking at this graph, okay, we're able to see it says as x approaches 2 to the left, and we'll get a graph that looks like this one up here. Hold on. Divided by Alright, so we have this graph right here. Alright, so if this asks what is the limit as x approaches 2 to the left? Well, if we look at this, we see that there's a vertical asymptote at x equals 2. And from the left, this is approaching what value? Positive infinity. Alright? And I'm not going to bother checking that with the table again. You could, if you wanted to, you can say on your calculator, you can go like this and check the value that's really close by going So 2 from the left would be like 1.99999. So if I check this out by taking this and going second trace, I'm going to calculate a value of, let's say, 1.9999. Hit enter. 10,003. All right. So obviously, if we can get big really fast. Okay.
Okay.
All right. So, questions on that? Looking at the graph is the easiest way. So, here's a little thing I'm going to see if you guys can get it. Right? After explaining to a student through various lessons and examples that a limit as x approaches 8, or 1 over x minus 8 equals that, I tried to check if she really understood that. So I gave her a different example. This was the result.
It's a silent 8, so it's silent 5 now.
Obviously, this is wrong. It is infinity, but it's just sort of making fun of the students, saying that, okay, they thought, oh, this is sideways 8, so I'm just going to make this into sideways 5. All right. That was it? Yep.
Man.
So, horizontal asymptote. Now, guys, we have another 10 minutes.
Okay, let's do that.
It's almost done again. What?
So, horizontal asymptotes. Okay? So what we're going to have, so this is when, instead of looking at limits that approach a certain number, like 2, 4, -5, or something like that, we're looking at what happens as x approaches infinity, or as x approaches negative infinity. We're trying to see what is happening way out on the ends of the function. Okay? And the notation that you're going to see is just limit as x approaches infinity of f of x equals, and the limit as x approaches negative infinity of f of x equals. Okay? And typically, a lot of times you will get to where it's going to equal a certain number, and other times you're going to get to where it equals infinity or negative infinity. Okay? So, and this is just essentially what I just said that for guys. We're looking at what is the end behavior of the function. Okay, so this is like the key question. This red kind of dark green, red, but maybe green, but not really. We want to figure out what is the end behavior of our function. All right, and you guys might be interested to know that you guys learned some Greek calculus. You just didn't know it. All right, this is going to be dealing with horizontal asymptotes, which you guys definitely knew. Okay, so again, you don't need to like write down all of this. This will all be, so what's the saying, as we go, so that's the positive values, you go further and further and further, so what y value is it getting close to? So I go further and further and further down the negative part of the axis, what y value am I getting close to? That's all it's asking. Okay, so looking at the graph. So if we look at this, we have, we don't even care what the function is. It's just h of x. So it says the limit as x approaches infinity of h of x. So, as x approaches infinity, so we get further and further out here. What y value is this function coming down to? 2. Okay, now, what is this value? This is the horizontal asymptote. All right, so looking at the graph, it's easy to see. So you come down here, this y value getting closer and closer to 2, as x gets larger. What about as x gets smaller and it approaches negative infinity? What's happening to the limit of h of x? Still 2. Oh. Huh. What's my horizontal asymptote? 2. Oh, that looks pretty cool. So if I know my horizontal asymptote, I know the limit as x approaches infinity, and I know the limit as x approaches negative infinity. Nice. we're gonna look at this next one. Okay, so if we go down here to this graph, what is the limit as g approaches, or what's the limit as x approaches infinity for g of x?
Wait,
What is the limit? So this is the graph of g of x. What is the limit as x approaches infinity?
what?
1, because as we get further and further out on that graph, it's getting closer and closer to this y value of 1. What about as x approaches negative infinity? 1. Okay, cool. So what's our horizontal asymptote? Nice. So, you know, the horizontal asymptote is equal to the limits as x approaches infinity or negative. Alright? Questions? Alright, let's look at what we got. Okay. We are going to stop. I'll tell you what your homework is. Calm down.